agent, environment, agent, state, rewards, and policy. So agent is interact with the environment, and in my case, my agent is need to control his support movement, and the environment is the system interact with. So in my case, the environment is physical or simulated world for his support, and the actions is possible move or decisions. And in my case, the actions for his part is leg movement or joint adjustment. And the state is current environment configuration. So in the disappointment simulation, the state is the body or and the leg position. And for the reward is the feedback after actions. So for my Hisabot, I make a reward for forward movement, stability, and effective. And for policy is the strict for action selection. So his support policy is learned optimal behavior over time. And the fundamentals of reinforcement learning. You can see the agent make the actions, and the environment will give the reward to the agent, and also the observation. So the agent can calculate the policy and make a next action for the reinforcement learning. So this component form a loop: observe, chose action, interact, receive reward, update policy, and enable iterative learning for effective decision making. So this is the reinforcement learning part, and next part is the robot. So I use a dimensional robot, and this one is a simple robot. So I make a 6 more motor to make the drive more degree freedom. Then for the frame, there's no frame we can use, so I make a 3D printer and print a new plastic frame for the robot. So for URDF, because it's a little bit difficult for me to just build up the URDF by myself, so I use Fusion 360 to combine the URDF and link all the joints together. And for the experimental setup, I use iSubDream for the training. So iSubDream is basically developed by NVIDIA for robotics and AI research. And the physics engine is for the high fidelity simulation. It's designed to support reinforcement learning and robotics experimentation. So the most important reason I chose iSubDream is it can support for complete articulate robots, and it supports multiple training, so it also use GPU to make the training time more less, so I can do more training at the same time. So for the reward function, I make some reward function for the robot. First one is the linear velocity. So the reward for velocity tracking in the XY plane. And another not in contact penalty, so it will make sure the robot will move with 6 foot or not just 4 foot or 2 foot. And the sine wave is just for making the robot move more smoothly, like move the feet like sine wave. And the observation part, is get the observation from the base linear velocity and also the angular velocity. And the common scale is the scale version of the commons give to the robot. And also the position scale. Scale different between current and the default position. And also the actions taken by the agent. And the top is the information for the robot's joint. So it shows some result here. So this one is the first time I try. You can see that's why I need to add the reward error time and the fatal contest penalty so that the robot will not keep jumping and put some foot in the air. And this one is the better one. You can see now the robot is moving more smoothly, but it's in the physics environment. So after that, I try to train it on the current environment. And at first, also the robot is not jump or not stable, but it's still not good. So I train a little bit. It's more like walking, but it's still not so good for the sine wave. So the future direction is I try to do the simulation to relative transform, and also is I try to fit 3 different objects with the 2 foot. The conclusion, reinforcement learning is making his robots smarter and more self-sufficient, helping them track different jobs and environments. So by learning from experience, this robot can adapt their flipping technique to different objects and then further enhance their versatility and problem solving capabilities. Thank you.
Any question? No question? Please go back to page 9 and 10. Okay. You list this item as the reward function. What is the total function of this angle or reward or penalty? I mean, what is the reward most significant? Which one is minor?
For the linear velocity and angle velocity, the torque and up reward is good for the training.
Yeah.
And for the other one, the air
And maybe the next page. The next page. Go down. Go down. I got. The iteration and the reward. Because you did not mark the different colors means what. So can you explain which one is your result or
It's like I've trained lots of times, and at the beginning the reward sphere is I set too much for the reward sphere, so the reward sphere is like 80 or 40, but the result is not good, and even the robot will stop with the point. So I try many times. I just level down the reward sphere. So you can see for the longest one, the orange one.
orange one?
Yeah, the reward is mostly like around 0 or under 10, but the result is the one I showed before. It's the better one. So I think it's also for the training time is not much the better. So I need to try and know how is the better result for the training number.
The iteration times seems like
20.
wow, 20
200
kilo
Yeah.
and 40, 60. So the iteration time so much.
Oh yeah, it's like
How many
Hour.
real time? It
around
takes?
hour.
Wow.
But it's not always have a good result. So
Okay.
I try to make the training time lower and
No.
see if the reward is better.
Okay, I see. No question? No question. Okay. Okay, thank you. We welcome the next speaker. Hi everyone, my topic is dynamic optical avoidance training and knowledge transfer for humanoid robots. My name is Ethan Liao, and my advisor is Ricky Pao. Can you make louder? Okay, great. This is my outline. I will begin with an introduction to the topic of my presentation. After the introduction, I will present the flow chart for specification. Next, I will explain the principle of inverse I-view transformation, followed by showing the result of the first I-view transformation. real-time simulation platform, enabling Rover to perform complete integration and learning in a safe and cost-effective setting. The knowledge acquired in training to avoid dynamic objects can also be applied to other robots to detect the velocity of dynamic objects in the real world. We apply the method that combines a bird's-eye view transformation with Euro to calculate the speed of moving objects within the frame. Why do we use BEV to detect the speed of moving objects? The main reason is difficult to obtain the actual distance of objects for the front view is due to perspective projection. In the front view, as the object moving future away from the camera, its size in the image gradually decreases. This effect is induced by perspective diminution, resulting in objects of the same size appearing to be the same size in the image, even at different distance. However, in the top view, the effect of perspective diminution doesn't impact movement, allowing the position of objects in the image to be more directly matched to their actual distance in space. This is speed detection function. Firstly, the frame from a video and resize the frame. Then calculate the transformation matrix for perspective transformation between images. And then use your detect moving object and calculate the object speed. The external parameters of the camera are divided into two parts. One is rotation and the other is translation. Rotation matrix is camera rotation represents coordinates of the rotation matrix. Rotation matrix is 3x3 matrix. Translation vector is 3x1 vector. It presents the line translation from the orange of the world coordinate system to the orange of the camera coordinate system. The left image displays how a point P, X, Y, Z in 3-dimension space is mapped to a point P, X, Y. On the 2-dimension image plane, the mathematical expression on the right are derived through the properties of similar triangle. By this proportional relationship, we can infer the relationship between the 3-dimension coordinate of point P, X, Y, Z and its projection P, X, Y on the image plane. This transformation matrix then converts image coordinate into physical coordinate. Its primary function is to obtain the vector distance corresponding to each pixel in the image. The transformation matrix is tensor form by install the object move in each frame to compute the object speed. Before calculating the speed, it is necessary to first measure the actual distance in the frame to convert how much actual distance each x and y pixel represent, and then divide by time to obtain the speed. Then see the result. I will use the footage from GoPro camera and the posted image to compare and calculate the NSC loss. And see the NSC loss result. The maximum velocity error is 6 or 7 centimeters per second, and the maximum angular error is 2 degrees. In a speed dictation study, we imply the BEV transformation and YOLO to detect the speed of dynamic object in video. This speed detection was conducted under the condition that the camera footage was stable without any shaking. However, in real-world environment, camera often encounter shaking or movement, which can affect the accuracy of speed measurement. And visual, I will train animal in iSubject to learn to walk, and then proceed to training it to avoid dynamic objects. The complete training result will be applied to other physical robots in the lab. Although we then to use the same training outcome to perform the test of avoid dynamic object as well. Thank you. Any questions? Please remember in Jackie's lab, ask some question, okay? Can you go back to page 14? Yeah. The MSD values for length and angle seems rather different. For angles, the MSD will indicate normally, but for length, it will increase in the later. 那个会上升到这里，因为它要结束的时候，它右漏最终的那个方法就会停，就是停在那里，所以它会跟GoPro camera 有差，就是因为GoPro camera 它可以对焦啊，但是它刚刚左边那个影片，它到右下角的时候，它还是对焦，但是它的方向它会变小，所以就会造成就是会变数字，对。还有另外 another question is, you use the real experiment for your research, right? 你是做真的实验嘛？不是用刚刚的模拟。对。因为你刚刚有说用到那个 iSub 它的一个平台 ，iSub 那个平台应该是模拟的。在实际的体现，然后要可以用在机器人，实验室的机器人可以躲避动态物体的。OK， 就是你那个是人形机器人，然后去比较。对。OK， 这个的话算是一个这个球的那个概念，它其实是要去模拟那个障碍物。对。OK， I see. No further question? Okay, thank you.
Shihan, and my advisor is Professor Sai. And today we talk about topic is research on the motion of a novel two-wheel robot based on an innovative reinforcement robot. And this outline, first I will talk about the motivation for this research. Then next the design of the hardware structure, and then it's the methodology. And I will try to use a kind of math to realize the robot movement. And I will show some result in demo part. And finally, I will conclusion and talk about future work. And my project has two parts to combine. And one is up body, and other is Diablo robot. And Diablo robot is a slick and vertical robot that combines the future of both bipedal and wheel robot. It's built on an open platform, which means it can be customized for different use, powered by 6 smooth, powerful motors. And its uniquely transformed feature allows the robot to balance the agility of the bipedal robot with the steady swiftness of a wheel robot. And I will utilize the grip function of the upper body human robot combined with the Diablo robot. Body should show perceive and understand things in different environments and take corrective action. This includes identifying and manipulating different types of objects and adapt to various terrain and obstacles. And this is my art body designed by SolidWorks and has a 28 bit of freedom. And now it's a Diablo bed. It's a really bipedal wheel robot. And this art body signification. And yeah, you can see the some specification. And this Diablo motor specification. And this is Diablo specification. And in maximum load in standing can hold 4 kg, and in gripping mode can load 80 kg, and also can do jump. And max speed is 2 meters per second. And my main controller is Intel CPU, and some controller is Diablo X3. The Intel Pro can control the up body motor and camera, and it also can communicate with the Diablo X3 Pro for movement control. And I will use reinforcement learning with iSubstring and have some benefits like it can show parallel simulation in iSubstring, enable thousands of parallel environments on a single CPU, and speed up learning with simulation data collection. In contrast, traditional simulation just only one environment at a time, and our benefit is cost efficient. Virtual training avoid physical wear and maintains cost, unlike a real robot hardware. Experiments that are and reset are essential, and while they require time and manpower, physical. Excellent safety. Virtual environment allows safe exploration in a hazardous condition without real harm. This aids in developer contingency space and improvement images respond without safety risk. And virtual testing provides a precise control over experimental conditions. Insurance with producibility. This is challenging in the physical world due to various influence factors. And this page represents the standard model of reinforcement learning. And in this cycle, the engine continuously learn by trying different actions and adjust its strategy based on the reward received, aiming to maximize its max reward over time. The end goal is to develop a product which is mapping from state to action. They can accrue the maximum sum of the reward across a series state. And in reinforcement learning have two different models, and you can see left picture is by hand in hexagon with PPO, and left picture is OP2 in Galibo with NFC. However, in my test, in my research, my text of reinforcement learning has not been completed yet. I will refer the math in the previous hand project to train my robot. And the main reward, like this, some position, two hand position distance, and two hand alignment, and action regulations, and such bonus. And if the object is full, I get some penalty. And this by this hand object, and he tried to use two hands to hold the cup, and he used four type algorithm to compare the HAPPO, MAPPO, MPPO, and SNC. And this is some demo with my project, and you can see first case is a flipping mode, and middle is a standing mode, and third is jump, you can jump. And in simulate stage, now I just put my agent to hexagon environment and put some desk and cup. Yeah, and final picture is my display effect will be this picture. And this is my conclusion and future. This project still under development, and there are still some small details need to adjust. For example, like the balance problem, because now he has a body to the diagram, so he need to adjust the balance. And the surrounding training result need to improve. And after then, using deep camera to implement navigation and visual function. If they use the algorithm to make the movement smooth and more perfect to achieve gripping movement. And final scenario, successful instrument simulation result on real robot. And finally, is the application. For example, in industry product line, maybe use this robot to do some gripping test. And this is my reference. Thank you.
Question? Okay.
How many degree of freedom and resilience sensor on your robot are?
My plan have one plan have a 9 degree of freedom and the three plan didn't have any sensor in RG2D this plan. Yeah.
This robot is a hybrid work between humanoid and real robot. So this type of how to name Diablo. Okay. So this type robot can have more functionality for maybe the manufacturer or some task. Can you use an example to explain the task for the type?
Maybe we can buy some upgrade. Yeah, and you can take the Diablo and put some to the robot, and also have some can do pointer to things to 然后
这个机器人它有什么样的特殊？
它的那个平衡很好，就是如果在战地模式的话，你踢它，它的演算法可以把它就是自动校正。
它刚还会跳。
对，还有跳，但是其实跳这个功能，实际上好像用处不太大，对，就是蛮炫的。
它底盘是轮子。
对，它的底盘就像轮组机械，像你看，
它是什么放？
它其实那个侧边其实是像一个人形，那它可以，它总共有6颗马达，那它可以
question is, in I see the reward 好像在下一页。OK OK。Okay. The reward. Your upgrade is PPO, right?
Yeah.
是粉红色那个吗
PPO in this project PPO.
PPO. Okay. PPO perform best, right?
Yeah.
Okay. So you use the upgrade PPO for your research.
Should say I will try to use the this. 因为其实我现在还没有真的完成，所以我会参照这个去把资讯往下。那实际上在实验室的研究里面，通常 PPO 的结果都会高于其他的方法。
所以应该可以这个。Okay. We welcome the next speaker. Thank you.
I'm Shubo Tang, and my professor is Jackie Bordis, and our lab is ERC. And today I'm going to share my research. My research is a kinematic optimization for robotic design, and I'm using machine learning techniques. This is my outline. First, I'll introduce my problem, and second, I'll talk about methodology, and third, I'll show my result and talk about my future work. So first is in the beginning of this research, our professor wants to use some motors we already have in our lab, and we want to make a new type of robot, which is different from the robot in our lab, like Torman or B3 is the humanoid robot. And so we found this interesting robot, which is Casey. Casey is developed by Agility Robotics, and it has some special features. I will show you the next page. And the advantage of Casey is that in his second version is digit, and is the only one robot using in factory before last year. Because last year is like a big breakthrough point for robotics. Here are some distinguished features of Casey. First, the walking. I can do dynamic balance during the walking, which is more like human, and it's quite good because the most of the robot before is it cannot walk that fast. And you also have a robot perception, which is Casey don't have any camera to sense the environment, and how it being robust to like go on stairs or walking on some obstacles is it will sensing the torque and force in its actuator. So actually it's balancing itself it's not like camera CD, it's just the torque and force to feel interact with the environment. And the last one is energy efficiency. This is their testing in the campus, and which is doing a 5K marathon, and it finished the marathon and didn't fail during the test. And so in some design point of views, there are 2 points I want to point out before this design. First is about the robot walking gate. They have 2 types of robot walking gate. First is dynamic, which is like Casey, and second one is static. Static walking gate is in each phase of the walking cycle, the robot center of mass will be inside of the polygon formed by the contact points from the ground. So it will be stable, but it cannot walk really fast. And dynamic walking is you will get some benefit from control floating and get more momentum
like like the OP3 in our lab, the leg is formed in two links and the motor is in each joint. The good part of this is it's quite easy to design, just put those motors in the joint and connect those links. But the problem, not really problem, the disadvantage of this one is that actually the motors is the most heavy stuff in the robot, and if it placed far from each other, you will have much higher momentum and it will be harder to rotate or swing. And if we use the forwarding as the robot leg, we can make the robot more impact, like most of the weight is in the motor part. In the hip part, it can be more compact and it will be less momentum if we want to lift the leg or rotate the leg. So here's my introduction of my problem. So in previous slide, summary short is that I want to use forwarding for the leg and want it to have dynamic walking. And so we have to start with the forwarding. First is if we just see the rotation of the forwarding actually is follow a trace. And this trace actually is defined after we define all the parameters of each link. You can see the trace changing if I change some length of one link. And the part of this is that we can see that the trace of this forward link is nonlinear and is more curvy. So now there's two ways there's two parts of kinematic for robotics. First for kinematic, and it's just it's easy to understand. It's like if we're given angle of the motor, of each motor, then we can calculate the endpoints of this robot arms or robot legs. And the inverse kinematic is doing the inverse way. We want the endpoints of the robot arms or robot legs in a specific place. Then we have to calculate what's the angle of each motor it actually have to move. And IK solution, we have two ways. First is the analytical solution, which is just use the math to do the inverse kinematic. But the problem is if we want to say want the robot legs move to a certain space like given x, y, or x, y, z, but it is impossible to use inverse kinematic just to calculate the inverse to get the angle of the motor. Only if we have the math equation, because math equation is actually quite complex. So actually, if we don't do the math equation, it is impossible to get this inverse kinematic. And the second part is there's another way theoretic solution, which is the Jacobian method. The problem of this method is calculation costly. I can show here the Jacobian equation looks like. Actually, it's quite huge. So the problem of this calculation costly is that you will slow down the calculation, and which means you will have more delay while trying to balance, and it's not good for dynamic working because maybe just 1 millisecond difference